When a critical part fails on something like a high-speed train, the results can be absolutely catastrophic. You can't just guess what went wrong. The only way forward is a precise, systematic engineering investigation. In this explainer, we're going to walk through a real case study just like that, breaking down how a really complex problem was traced all the way back to its root cause, and then solved permanently. A scenario like this brings up a massive question for anyone who operates a fleet. When a key component fails out of the blue, what's the process you can actually trust to make sure every other vehicle out there is safe? That's really the core challenge we're diving into today. Okay, so our story kicks off with the exact kind of event that engineers work their entire careers to prevent. We're talking about a critical component failing, not in some controlled lab, but out in the real world, during live service, creating an immediate and serious threat. To be specific, a traction motor mounting bracket just fractured. Now, this was not some small issue. It had the potential to cause a catastrophic event, which, as you can imagine, shot this problem straight to the highest levels of the organization. Suddenly, the safety of the entire fleet was a huge question mark. So the engineering team was immediately facing a two-front battle. First, they had to fight the immediate fire. Figure out what to do right now to manage the risk and keep the fleet running safely. But at the same time, they had to win the long-term war. Develop a permanent, fully validated, safe life solution so this could never happen again. So, how did they even begin to tackle this? Well, not with hunches or theories. They used a rigorous, multi-stage analytical investigation. The whole idea was to methodically peel back the layers of the problem and just let the data show them the truth. The investigation followed a really classic three-step process, where each stage builds on the one before it. First, they built a digital simulation of the failure, using finite element modeling, to get a handle on the theoretical stresses. Then, they took those models into the real world with on-track testing to validate them. And finally, they did a deep dive on all that data to find the definitive root cause. That initial computer model, the finite element analysis, gave them their first huge clue. It showed that the bracket was extremely vulnerable to failure from sideways or lateral loading. This was a critical piece of insight because it told them exactly where to focus their physical tests. This is where the real detective work happened. The on-track testing used a process of elimination to zero in on the problem. They tested the component with the cardan shaft attached and then without it. The data was crystal clear. When they removed the cardan shaft, it confirmed that an imbalance in the shaft itself was the main source of those damaging, high-frequency vibrations. So all this data collection was pointing the team in a very specific direction. The on-track tests had shown them what was happening, but now it was time for the deep data analysis to reveal exactly why. The key that unlocked it all was a tool called spectral analysis. In simple terms, this method takes all the complex, messy vibration data recorded over time and turns it into a clean chart of individual frequencies. It allows engineers to see exactly which frequencies are carrying the most destructive energy. And here it is, the aha moment. The analysis showed that the natural vibrating frequency of the motor's rubber mounts was a perfect match for the rotational speed of the cardan shaft when the train was at its typical running speed. This created a destructive resonance that just amplified the vibrations to dangerous levels. It's just like pushing a kid on a swing. If you push at exactly the right moment, each tiny push adds more and more energy, making the swing go higher and higher. Pinpointing resonance as the root cause was the huge breakthrough. Now the team could finally pivot from investigating and analyzing to what they do best, engineering a robust, permanent fix. The immediate fix, the Band-Aid, was a super strict and expensive inspection program to catch cracks before they could grow. But the permanent solution, well, that was much more elegant. It tackled the root cause head-on with redesigned brackets, new motor mounts that were optimized to change that resonant frequency, and a brand new monitoring system. The ultimate outcome here was so much more than just a new part. It was a fundamental shift in philosophy, a move away from that endless cycle of reactive repairs and toward a future of proactive, data-driven design. So, what's the tangible result of all this work? It's this number, 30 years. The final, validated design was so robust, so reliable, that it was certified for an unmonitored safe life of 3 decades. That means long-term safety and fleet availability are ensured, completely eliminating the original risk and all those costly inspections. This whole case is such a powerful demonstration of a few key things. That systematic analysis is absolutely essential, that you need a multifaceted approach combining digital models with real-world tests, and that the ultimate goal should always be a validated, safe life design. And all of this leaves us with one final important question, really a question for you. How can your organization use this kind of predictive analysis to finally move away from reactive maintenance and get to a place of proactive, intelligent engineering?